The next topic for solids is slope and deflection. And we are going to learn two methods for this. The first one is double integration. Good job. All right. Equations here are EI d to the fourth v over dx to the fourth is the load. EI d cubed v over dx cubed is equal to shear. Please note that this is a lowercase v and this is an uppercase v. Little v is for vertical deviation. Big V is still for shear. Okay, those are two different V's there. All right, and then EI d squared V over dx squared is equal to the moment. EI dv over dx is equal to the slope. And EIV is equal to the elastic curve, or the deformed shape of a beam. Okay, now we have seen this before with moment equations and shear equations in terms of x. Shear of x is equal to the integral of load. If you prefer to go the integral way instead of the derivative way, moment x is equal to the integral of shear. Slope of x is equal to the integral of moment. And the vertical deviation is equal to the integral of slope. All right, now with shear and moment and load, the make and model of the beam don't matter. But if I have a 2x2 square beam and a 2x2 steel beam, those two things are going to deflect quite differently. So when we get to slope and deflection, we add in E and I. E is still our modulus of elasticity. And I is still the centroidal moment of inertia. For the cross section. Okay, these are the same E's and I's that we've been using for our stress calculations, okay? So we can either work it bottom to top with derivative, but how we're actually going to be doing it is top to bottom with integrals, because we can get shear and moment equations in terms of x. We did that towards the beginning of the semester, and we're just going to integrate those twice for moment and slope. Okay, so my first example is going to be my favorite, the simply supported beam with an evenly distributed load. So here is my beam. I'm going to put a pin and a roller and a distributed load on this beam. Okay, and I'm going to give the load a magnitude of 150 pounds per feet, and I'm going to have it act over 10 feet. A and B. All right, now if I'm talking about vertical deviation, okay, I'm going to put some coordinates on here. Coordinates? Anyway, X. And Hibbler calls the Y direction, in this case, V, because vertical deviation is what we're talking about, so we're going to define the vertical direction. So in this case, it's the up direction, up and down, okay? I want to find the equations for slope and the elastic curve. Okay, so I want to find equations for slope and the elastic curve. Now the elastic curve is how the beam deforms. That's why we're talking about vertical deviation. So if I'm holding it up on two ends and loading it in the middle, then this thing is going to want to bend down in the middle here. So this red line that I've drawn is the elastic curve, or the deformed shape of the loaded beam. Okay? Slope is going to be slope at any place on the elastic curve. So if I look at this random point here, and I draw a tangent line to it, poorly, let's try that again. Okay, then this right here is going to be my slope. So the equation is going to be, I can find slope at any point along my elastic curve. Okay, so those are the things that I'm looking for. Solution is going to start exactly like shared moment equations in terms of x. Okay, I'm going to have one set of equations because I only have one load acting along the entire length of the beam with two supports. So I'm going to have one section here. Okay, because this is symmetrically loaded and symmetrically supported, my reactions are going to be symmetric. So this is 750 pounds on the left side at A, and 750 pounds on the right side at B, and AX is going to be 0 because I don't have anything acting in the X direction. All right, so I'm going to need a free body diagram of my section. Free body diagram, section 1, and I'm going to take it to the left. Okay, give myself enough space down here. So here it is, just a representative section. There's no specific distance because 0 is less than or equal to x is less than or equal to 10 feet, okay? X is representing a whole range of values. And I have pin A here, 0 and 750 pounds. So this is all going down at A, and then I have my distributed load here, 150 pounds per foot, and then I have my internal forces, shear, normal, and moment, and if you so desire, I need my distance x here. I'm going to go ahead and put this in blue, x, and remember x represents the entire range from 0 to 10 feet. Now as we're looking towards the left, pin A is 0 to 10 feet. Now I'm putting this equal sign here because we're now talking about slope and deflection, and both will be represented at I don't know how to write that out, but both will be the same at B, at 10 feet. So I want that equal sign to be there for slope and deflection, okay? Now I'm going to use deformable body equilibrium, summing forces in the, oh, I don't even need V. Let's just go straight to moment. Why don't I need V? Because slope and deflection is what I'm looking for, and they are based on the integrals of moment. So I'm just going to go straight to the moment equation. Summing moments about my cut is equal to 0. Counterclockwise is added to the equation. 0 is equal to minus 750 acting at a distance x plus my distributed load 150x, and it is acting at a distance of x divided by 2, and then plus my moment. So my moment equation is equal to 750x minus 75x squared, and this will be in pound feet. Okay, so this is what we did with shear and moment equations way back at the beginning of the semester. Okay, now I'm going to integrate that. So my slope equation, and I want to throw EI in there because slope is going to change based on the material E and the cross section I, is equal to the integral of the moment in terms of x. So this is going to be 750x squared divided by 2 minus 75x cubed divided by 3 plus a constant of integration. I'm going to subscript that with a 1 because we're going to end up with 2 here. And this will be in pound feet squared because we're taking the derivative in terms of x. X in our case is a distance, so that is going to increase that value. Okay, and then we have vertical deviation. Again, this is lowercase v for vertical deviation, and that is the integral of the slope equation, dx. So that's going to be 750x cubed divided by 2 times 3, which is 6, minus 75x to the 4th divided by 3 times 4, which is 12, plus c1x plus c2. And this will be in terms of pound feet cubed. Again, we're integrating in terms of x, so that's going to increase the x distance value. All right. These aren't my answers because I need to solve the constants of integration. Constants of integration are found with boundary conditions and continuity conditions. Continuity is not a problem here, so I can just solve this with boundary conditions. Don't worry, we'll do one with continuity in a little bit. So boundary conditions are where we know the answer. Okay, so where do I know slope is equal to 0, and where do I know vertical deviation is equal to 0? Well, coming back up here, the whole point of the pin and the roller at A and B respectively is to hold the beam in place and not allow vertical deviation. So my boundary conditions are pin A and roller B have V equal to 0. Again, lowercase v for elastic curve, not capital V, which is shear. They do both have shear, but they do not have vertical deviation. Okay, and that's always true. Whenever there's a pin or whenever there's a roller, the vertical deviation is going to be 0. So my pin is at x is equal to 0, and my roller is at x is equal to 10 feet. Okay, how do I know that? Coming back up here, here's my origin of the coordinates. I drew it at A, right? Oh, highlight that. It's really ugly and bold now. Okay, so A is at x is equal to 0, and B is at x is equal to 10. Okay, it's a datum if you prefer that value. Okay, so let's plug that in. So here's my vertical deviation equation. So 0 is equal to 750 times 0 cubed divided by 6 minus 75 times 0 to the 4th divided by 12 plus C1 times 0 plus C2. Okay, so this first 0 is our vertical deviation. Okay, and all these other zeros are our location x. Okay. We are going to find with this equation that if we solve for C2, it is going to equal to 0. That is not always the case. It just happens to be the case for a simply supported beam with an evenly distributed load with the origin at A. Okay, next up is my pin at B. So we have 0 for the vertical deviation is equal to 750 times 10 cubed divided by 6 minus 75 times 10 to the 4th divided by 12 plus C1 times 10 plus C2 that I'm going to plug in there as 0 so that you know I'm using the same equation and where all the little values are. And doing this algebra, we find that C1 is equal to negative 6,250. Okay. Okay, great. So we're done. Let's just plug it in. So my answer, slope EI is equal to 750 divided by 2. Oh, I didn't write this out. I'm so lazy. x squared divided by 2 plus, nope, minus 75 divided by 3, that's 25, minus 25x cubed minus 6,250, and that'll be in pound feet squared. And then my vertical deviation, EI, why'd I put that in parentheses? I didn't do the other one. VEI is equal to 750 divided by 6. So this is 125. Yeah, x cubed minus 25 divided by 4. 6.25. Oh, good job. 5x to the 4th minus 6,250x, and this will be in pound feet cubed. I'm sorry, I don't know where my brain is. 375x squared. Okay, did I get all those numbers correctly? 75 divided by 12. Okay, so there's my final answer. Oh, and all of these are limited to 0 less than or equal to x less than or equal to 10 feet. If we're outside that range, these equations no longer apply.